Hello students, in the previous video or lecture we have seen the separately excited DC generator. We have seen the circuit. Important question is separately DC generator. We have seen the applications of a separately excited DC generator and we did some examples. So our next point is the second type of DC generator called shunt DC generator. The word shunt means it's simply parallel, right? So in this type of DC generator, the field windings, and the armature winding or circuit, they are connected in parallel. See, the armature, the field circuit and the armature circuit, they are connected in parallel. So such type of DC generator, we call it the shunt. What makes it different, this shunt, is it will supply its own field current. The field, the voltage or the supply Vt will be supplied from the generator itself, and the field is excited by the terminal voltage Vt of the generator itself. So a generator that supplies its own field current, by having this field connection directly across the terminal of the machine, it is called shunt DC generator. So the whole terminal voltage is going to be supplied for the field. It means full terminal voltage is applied across the field. So the nature of this field, or the kind of winding of this field winding in a shunt, is it is a fine wire type, very fine wire type with large number of or many number of turns, with a many number of turns. So therefore a very small current is supposed to flow inside this IF. Why? Because the number of turn of this type of wire is large, but it is fine wire. If it is fine wire, the cross-sectional area is going to be very small. It means resistance will be very high. So an order of 100 ohm resistance we're going to have. Therefore, the current is IF is going to be very small. So this shunt type of circuit connection, from our circuit background knowledge, we can write KVL for this circuit. So we can get V terminal is going to be EA or EG minus IA RA, KVL. And if you try to write KCL on this point, KCL, entering current is equal to leaving current. Therefore, I is going to be IF plus IL. This is another important question. Obviously, this field current is in parallel to this V terminal. So IF is going to be V terminal divided by RF. These are a very important question in the shunt circuit, what we have to remember. And power is similar with the separately excited, what we calculate before. Power derivative is EA or EG times IA, and the power input obviously VT times IA. This is similar. So one of the advantage of this shunt DC generator is that since it is supplying its own field current, we don't need external power supply. We don't need external. This is a distinct advantage of a shunt DC generator. It is supplying its own field winding. Now the question is, when the generator is starting, and if the generator is supplying its own field current, how the generator will start? From where this Vt on the initial is going to be found? How it will start? That is a question that needs to be answered in a shunt DC generator. So, if the generator supply its own field current, how does it get the initial field flux? Because Vt is not yet supplied, so how to get initial field flux? The question is, the answer for this question is the residual flux, what we have discussed in a separate course. So there should be the residual flux inside the generator. If there is no residual flux inside generator, means there is no EA or EG, no generator. If there is no EA, there is no VT. If EA is 0, VT is definitely going to be 0. So unless and otherwise the generator is new, there should be a residual flux. Once the residual flux is there inside, definitely the generator will generate the initial flux. How? See, you remember the equations. Now, let me explain this a little bit. Now, in EG or EA is going to be K omega, for example. This is a residual we said, right? And we know VT is going to be EG minus IA RA, we say. And IF is going to be VT divided by RF. Now, if there is a small residual flux inside our machine, there will be small internal generated voltage EG. If this EG is there inside the machine, it means smaller EG is there inside the machine. Smaller EG means it will produce smaller VT, small VT. This small VT going to produce another IF. Now, here small VT, smaller VT. So this smaller VT is going to produce some IF flux, smaller IF flux. This IF flux is the one which is responsible to create the flux inside the machine. Now the flux created with this small IF, let me say I1, I mean phi 1. Therefore, on the second round, EG1, I can say it is going to be K phi of residual plus phi 1 omega. Now, this EG1 is greater than obviously EG. So this keep on or little bit higher than EG. Why? Because the flux inside the machine is increased already. Now this R residual plus phi 1. This is the initial flux, and this was the flux created by this residual flux. Then it will keep on increasing EG. So the amount of voltage, the voltage at the right on the beginning, the voltage appear at the terminal of the generator, it is supposed to be 2 volt to 1 volt to 2 volts. It's very small voltage. But when the voltage appears at the terminal, it causes current to flow in the generator field coil. So this IF will be created. This IF will produce flux, additional flux. If additional flux is created inside, it adds together with the residual flux, then total flux now become more, generating more voltage. Now more flux is there, which is flux residual plus flux 1, what we say, flux residual plus flux 1, what we said. So it will be gradually building. So it increases the flux and it causes an increase in EG or EA. Then if EG is increased, VT will be increased. VT increase means IF will get increased. IF increased means flux will get increased. So it will build gradually through this step. So in a real generator, the voltage does not build up in a discrete step. Instead, both EG and IF or IA and IF increase simultaneously until it reaches the steady state condition. It simultaneously increases. But for our understanding, we'll see how the gradual stepwise the voltage will be built in a shaft DC generator. Let us see a little bit how the voltage is building in the shunt DC generator. Now see this curve. This curve is EA versus IF curve. So to show how this gradual voltage increment in a shunt generator, let us see this curve. This is IF curve, and this is going to be either VT or EG. Now, sorry friends, now the two important curves we need to plot. What are they? One is the saturation curve, open circuit curve, which is starting from certain point, like in this case D, and this is the origin O. And we have another important curve called field resistance line curve. Field resistance line curve means it is simply the RF, which is going to be VT divided by IF. So having this some terminal voltage and current, if you try to plot the resistance, it will give you linear relation like this. So this is an open circuit curve, and this is the field line curve, what we call it RF curve. RF curve, which is VT by IF. VT by IF. IF. So now to just show you how this voltage building process is happening in shunt generator, like we have seen in a separately excited type of our generator, even though the current IF, I'm sorry, even though I'm sorry, this is IF. So like we have seen in this is my array. So though the current is zero, the internal generated voltage is going to be have some value, this some value which is going to have. So right on the beginning, our EG generated voltage or VT is going to be OD magnitude is there. Due to what is this? Residual flux. Due to the residual flux. Then if there is EG, some ODEG is there, we know from the equation EG, it is going to be K phi omega due to residual. Now this EG is already generated internally, and from the equation of the shunt, we know VT is going to be EG minus IA RA. Now, this internally generated EG, very small EG due to residual flux, it will generate or it will increase VT. Now, here EG is there. EG is already very small. So, it produces very small VT. VT will be there. I mean, this is different from zero. This is different from zero. So, VT is there. If VT is there, it will produce IF, which is VT by RF. Now, this produces IF. This smaller VT, it produces IF. How much? For example, this is an IF curve. So to produce smaller amount, like we can say this maybe F1 right? It produce smaller IF. What is the consequence of IF? Now, if IF is increased inside the machine, this IF will going to produce a flux inside the machine, additional flux created due to IF. Let me say flux 1, right? Flux 1. If flux 1 is created inside the machine, remember that previously there was smaller residual flux. Now, due to this consequence, additional phi 1 flux is created inside the machine. This IF1. Now the next, what is the impact of this phi 1? It will produce or it increase the range of, the magnitude of Eg1. Now Eg, let me say Eg1 is going to be K I residual plus phi 1 times omega. This is omega, okay? Omega. Sorry. And this is omega. So it produces a new voltage inside K I residual phi residual phi 1 omega. Now Eg is increasing to new value. It means Eg is increasing to new value. We call this Eg1. So due to this current IF1, the new flux is created that is going to be the summation of the two. Eg is going to be created. So new voltage, what we can say Eg1 is generated inside. Again, if Eg1 is generated, it will repeat this step. If Eg1 is increasing, if we say this Eg1, if it increase, Vt again increase. If Vt increase, let me use different color. Now second round, if this Eg1, if this increase, again Vt will increase again. If Vt increase, IF again it increase. If IF increase, it produces a new or another flux inside the flux. What this flux is going to be increased, we may say this flux is maybe phi 1. See, this flux maybe, phi 2. Therefore, phi 2 again it leads now this IF, the newly increased IF, it produces some current. This Eg1, it produces a new IF. So the new IF will going to be this much. So I can say this is IF2, which is created due to Eg1. Then if Eg1 create IF create another flux, this IF flux produce another generated voltage. I can say this Eg2. This Eg2 again, it produce another current called IF2. IF3, let me say. Like this, it will build gradually and stop when it reaches this point, what we call important point. So if you see the way this signal is, the voltage inside the generator is built, it seems like a ladder. See, it was starting from this. See, and start diminishing and stop here. So it is showing a stage. So practically I said everything will be built simultaneously, but logically they build gradually. So the final stable point or operating point M will be the point of intersection between the no load curve and the field resistance line. So our generator is building in between these two important curves with a step of stair type. So what will happen if we increase RF? If we increase the RF, obviously, if the field circuit resistance increases, the final voltage decreases as a point of intersection tip toward the left. If we take different value of R and try to plot, it will have different field resistance curves. So obviously R naught is less than R1, R1 is less than R2, R2 is less than R3. So it will shift like this. If the R naught or the field resistance is less than this curve, it will take long time to build. See the area of this curve R naught and R2, it will take long time. If the area is very small, it will take short time. What will happen if the R or field resistance is greater than this curve, what we call OCC curve? OCC curve means R3, for example, it is out of the OCC curve, so there is no intersection point, so the shunt generator will not build the voltage. So the field resistance line, which is tangential to the OCC curve, we call it a critical field resistance, because this resistance R2 is critical. Above that, the shunt generator will not build the voltage because there is no intersection point. And below that, based on the area, it may take from small or short time to longer time, it can build. So we call this value of resistance, it is a critical field resistance. Sorry friend. If the field circuit resistance is more than the critical value, the machine will fail to build the voltage. So that no voltage will be induced inside the machine. The reason is there is no intersection point between the OCC curve and the field resistance. So why shunt generator fail to build voltage? Why they are supposed to fail to build the voltage? There may be three reasons are mentioned usually. One, there may be no residual magnetic field in the generator to start. That may be one reason. As we said previously, if there is no flux from that important equation of EG, obviously, if there is no flux means machine is there, we are rotating the generator with a certain speed, but EG will not generating means this flux is maybe zero. It may be zero. Therefore, one reason may be there is no residual flux. So what is the solution if it happens? If we came to know that the machine has no residual flux, what we should do? We have to disconnect the field winding from the armature, disconnect it, and directly connect to the external source, maybe batteries, so that the current will flow through the field winding. It may leave some residual flux. Inside the pole, which will then allow normal starting. If the machine gets residual flux, small residual flux, it can start by itself. Such techniques by which we can start the DC machine, it is called flashing of DC machine. We call it flashing. Simply flashing means disconnecting the field armature the field winding from the armature and connect it to external supply battery. That is one solution. Second, the direction of the rotation of the generator may have been reversed. It means the field winding direction and the armature winding direction, they may have connected in a reverse manner, so that when the residual flux start creating the first EG, and EG will create VT, and that VT will create IF, rather than adding together, it start reducing because the field is opposite. So this problem may cause the DC shunt generator may fail to build the voltage. So in this problem, if this problem occurs, it can be fixed by reversing the direction. Simply reversing the field polarity, it may build the necessary voltage. And the third and the final possible cause for the DC voltage, DC generator to build initial voltage is field resistance may be adjusted to a value greater than critical resistance, like we said previously. So if the field resistance here, if the field resistance or a if the field resistance is beyond the critical value out of the OOC curve, so there is no cross-section point in between, so it may fail. It may fail to build. So it might be the field resistance is higher. So what is the solution for this? We have to reduce the field resistance. If we reduce the field resistance, means reducing the field resistance means we are trying to pull down and get the field resistance inside the OCC curve, either here or anywhere. If we reduce it, then it will start building the voltage required for the DC generator to start. That is the main cause and solution for the DC shunt generator, the DC shunt generator to build the internal required voltage, the internal required voltage. And next time we'll going to see the characteristics or the behavior of our DC shunt generator. This is going to be covered on the next section. Thank you for listening.